Hi everyone, in this video we are finally going to start discussing how we figured out that we were seeing a depletion of our stratospheric ozone. But in order to do this, we absolutely need to review how we naturally create ozone in our atmosphere. So we start off with diatomic oxygen, and we know in the presence of UVC light, or any light that has, any UV light that has wavelengths of less than or equal to 242 nanometers, our oxygen that has that double bond splits in half and we create two monatomic oxygen atoms. Now, these atoms then interact with other diatomic oxygen molecules. When they come together, they create an ozone molecule. So now, what we can essentially say from this mechanism is that our concentration of ozone is directly proportional to the amount of sunlight that oxygen receives, or the amount of sunlight that our Earth receives. So when we think about our sunlight or our solar power in terms of coming from the sun to the Earth, we need to think of it in three different very important factors. So the first one is just in general, when does our planet receive the highest intensity of sunlight? Highest intensity of sunlight. So essentially what we're talking about here is how far away is the Earth from the sun. So we know that when our Earth orbits the sun, it moves in kind of a unique pattern. At some points it is very close to the sun, and there are other points when it is farther away. So when our Earth is very close to the sun, we are receiving a lot of that natural solar power, or that sunlight from the sun, and so in theory our ozone concentration would be really, really high. However, when the Earth is farther away from the sun, it's not going to receive as much of the sunlight, so again, in theory, our ozone concentration should be significantly lower. So what we can map out are two different points on Earth where we can see this high intensity. So the first one is at our equator. And so at our equator during equinox, we actually see the highest amount of sunlight in March and October. Now, alternatively, for the rest of the planet, so I'm just going to write others, everywhere else, it is just during summer solstice. Summer solstice. Now, we know that that is different based on your location or where you live. So if you live in the northern hemisphere, your southern solstice is during, or your summer solstice is during June. If you live in the southern hemisphere, your summer solstice is in December. Okay, so that's when we get the most amount of sunlight on Earth based on our distance, from Earth and the sun. Our second factor that we talk about is the angle of the Earth. So we know that the Earth spins on an axis, which means that we're not just saying here's our sun, here's our Earth is actually slightly tilted. So based on the way of its angle and that tilt, we're going to see a difference in the amount of concentration of sunlight that the Earth actually receives. So for example, if it is tilted this way, we would say that the amount of sunlight that reaches the Earth is going to be highest in the lowest section down here. So in theory, this part would have the highest concentration of ozone. On the opposite effect, if it's turned, we know that then this top part right here is going to receive the most amount of sunlight, and so the ozone concentration up here would be the highest. So what we need to take from this is that in general, so we're going to say globally for the entire Earth, our highest amount of sunlight based on the angle of the Earth is going to be in January, where our lowest amount, again based on the angle of the Earth, is in June. Now, the last thing we need to talk about are these things called sunspots, which I'm sure you've heard of before. But essentially, there are sunspots on the Earth that kind of changes the amount of electromagnetic radiation that the planet, or our planet, Earth, actually receives. And so based on these sunspots, the amount of sunlight is going to fluctuate from anywhere between like every 11 to 12 years. And so just based on whatever decade you're in, we're going to see a difference in the sunlight. However, it doesn't attribute too much to the difference of sunlight in the Earth, but it absolutely does affect it a little bit. And the last thing I want to throw in here are wind patterns, because the wind patterns highly affect the amount of ozone concentration and where you are on the Earth. Even though it's not directly affected with the sun, I do want to include this in here because in your brain, I want you to be thinking of all four of these factors. We're going to go back to these later, but just start putting them in your mind of this is how our sunlight affects our ozone concentration. Now, we started measuring ozone concentrations way, way, way back in 1926. And when I say we, I mean the Swiss Meteorological Institute. So actually I wasn't doing this. obviously. All right, but then what was really neat, in 1979, we finally started using satellites. So we actually started doing measurements of our ozone concentration from our upper atmosphere. So we use satellites, we use high-flying planes, we use all these really cool things to get very, very good measurements on these ozone concentrations. Now, if you recall, we discussed earlier that we measure our ozone concentration in these things called Dobson units, okay? Dobson units, typically we just write it out as big D, big U. So what we need to remember is that 1 Dobson unit is typically equal to 1 ppb. Now when I say 1 ppb, I mean we have 1 molecule of ozone per every billion molecules of air. But let's put this into perspective here. When we are at the equator, we measure anywhere between 250 and 270 Dobson units of ozone. When we move up like a little bit north or a little bit south, okay, so we're no longer at the equator, our measurements are anywhere between 300 and 350, again in Dobson units. Now, when we go all the way up to our northern latitudes, okay, I'm being very specific about our northern part, we can actually have measurements all the way up to about 400, and we've even seen some a little bit higher than 400, which is really, really high. However, we have also noticed that we have this gigantic hole over the Antarctic. And like, what is going on with that? They couldn't figure out where it came from. They couldn't figure out what it was. When they first started actually doing these measurements, they thought that their instruments were broken because they were getting such crazy measurements for their ozone concentration in the Antarctic. We're going to come back to that later, but for right now, let's just see if we can figure out something. So in 2014, they had a measurement of 220 Dobson units, okay, so way not even close to 400, in Antarctica. And what I want you to do right now is to just convert 220 Dobson units to a ppm measurement. So what is 220 Dobson units in parts per million? Go. All right, did we get an answer? Hopefully you did. There were several different ways that you could have attacked this problem, so I'm just going to show you one way that I personally would have done it. So we learned earlier that 1 Dobson unit is equal to 1 ppb. So right away I would have just said, okay, 220 Dobson units is equal to 220 parts per billion of ozone. So now all you had to do was go from parts per billion to parts per million. And so the best way to do that is just to set up 2 relative fractions. So 220 pieces of ozone per a billion, so 1 times 10 to the 9th molecules of air, is equivalent to, I'm just going to use an algebraic x, all over million, 1 times 10 to the 6th. So we are saying here 220 parts per billion, and we're trying to convert to an equivalent number in parts per million. So we use million down here, billion down here. And if you solve that out properly, you would then see that x would be equal to 0.220 ppm. So the correct answer was 0.220 ppm. Hopefully that made sense. If it doesn't, take a second and figure out a way to convert from ppb to ppm. Have a great week. Take care of yourself. Drink water.